Let's compare factoring polynomials over rationals and over integers. The idea is simple. Any equation over z stays valid over q, and I can clear denominators over q to get an equation over z. This is how we'll see shortly that zx is a UFD using unique factorization in z and in the PID qx. The point is that constant factors are the only issue when we compare factoring over z and over q. For example, 10 is a unit in q and so in qx, but it does factor non-trivially over z. So let's take an integer polynomial of positive degree. Now one might hope that it is irreducible over z if and only if it is irreducible over q. This is not quite right, but it can be fixed. So see if you can find the right statement. The backward implication is true, but the forward is not, and for a simple reason. For example, 2x is irreducible over q because 2 is a unit here, so it doesn't count, but 2 times x is a non-trivial factorization in zx. However, this is the only problem, and to fix it we make a definition. We call an integer polynomial primitive if the GCD of its coefficients is 1. Notice that a monic polynomial is automatically primitive. And now, if I start with a primitive polynomial, then the forward direction is also true. To prove both of these claims, I have written them here in the contrapositive form. Keep in mind that both versions of this claim are useful, so you should remember both of them. For this, it may be useful to keep in mind some simple example, like this one, to remind you what restriction is needed. Okay, so let's see the proofs one by one. Suppose I start with a primitive polynomial f0. I cannot pull out an integer factor. So if this polynomial f0 factors over z, both factors must have smaller positive degree. So the same factorization works over q. The other direction is more interesting. I am saying that if I start with any integer polynomial, if it factors non-trivially over q, then it must already factor over z. I have begun the proof over here. See if you can finish it. Before proving number 2, let us see this lemma of Gauss. It says that the product of two primitive integer polynomials g0 and h0 stays primitive. This small lemma is the only new idea we need to understand this comparison. So let's see the proof. Suppose the product g0 h0 is not primitive. That means the GCD of its coefficients is not 1. So this GCD is divisible by some integer prime p, and p divides g0 h0. Now reduce coefficients modulo p to get this map phi from zx to fpx. By assumption, phi of g0 h0 is 0, but phi of g0 and phi of h0 are both non-zero because g0 and h0 are primitive polynomials. For a primitive polynomial, at least one of the coefficients must be not divisible by p. Also, phi is a ring homomorphism. So I have the following situation in this target ring. I have two non-zero elements whose product is 0. But fpx is an integral domain. So this is not possible. That means my assumption was wrong. So g0 h0 is primitive. You should understand this proof properly. It is possible to rewrite it differently by explicitly writing g0 and h0 and taking the highest or the lowest coefficients that are not divisible by p. But this way of writing it is neater. Also, in general, going modulo a prime ideal is a standard technique in ring theory. Okay, now you should go back to number 2 and try to prove it again. I have written a proof over here, but it is incomplete. So try to see where this lemma enters the picture. I am given an integer polynomial f0 with the assumption that it factors in qx. So suppose f0 is g times h, where coefficients of g and h need not be integers. but I can clear denominators. So for g, I take out the product of denominators, and then from the resulting integer polynomial, I also take out the GCD of coefficients. So I get a primitive polynomial g0 times a rational number. You should check that this expression is essentially unique, which means g0 and this rational number can only change by multiplication by units in z. Okay, I do the same thing for h and I plug in these expressions into this product to get this equation, which is a priori only over q. But I claim that this rational number is actually an integer, which would finish the proof for me. So let's see why this is the case. To get to integers, I multiply by uv to get this equation. And this now is an equality of integer polynomials. So the GCD of coefficients on the left hand side and on the right hand side must be equal up to associates in z. So let's separately look at these GCDs. On the left hand side, the GCD is visibly divisible by the integer uv. On the right hand side, g0 times h0 is a primitive polynomial by Gauss Lemma. So it cannot contribute to the GCD of coefficients. So the GCD of coefficients on the right hand side is AB and no more. So I have obtained that uv divides AB, which is exactly what I wanted. Okay, here's an example illustrating what is going on. To factor this polynomial, I first took out the leading coefficient and then factored this monic polynomial over rationals. But then when I cleared the denominators, they automatically cancelled out and I got an integer polynomial which was guaranteed to me by number 2. We can now give a first answer to this question. Irreducible integer polynomials are of two types. In degree 0, I get the ordinary integer primes, and in positive degrees, I have primitive polynomials that, when we regard them as rational polynomials, are irreducible in this PID. You should check that item number 1 on the previous board shows that these are indeed irreducible, and the harder item, number 2, which required Gauss Lemma, shows that there are no others. Okay, this is nice, but with just a little work, I can get a nicer result. Remember that Zx is not a PID, but it still has unique factorization. To show this, I will first check the chain condition on principal ideals or equivalently on factors. As I keep taking successive factors, at every stage, either the degree goes down, and this cannot happen indefinitely, or the GCD of the coefficients is a proper divisor of the previous GCD. And this too cannot go on indefinitely because Z is a UFD and so it satisfies the chain condition on divisors. Okay, to show the next condition, it is easy to do it for integer primes. Just do it by hand or use this isomorphism. To prove this condition for second type of irreducible elements, I have made a start here. See if you can finish the proof. I want to show that this irreducible integer polynomial of positive degree is prime. So I need to show that if f0 divides g0 times h0 in zx, then f0 has to divide one of them in zx. For this, I take help of qx. Now qx is a PID. So it is a UFD and therefore every irreducible element there is prime. Now f0 is irreducible in qx and this divisibility stays valid in qx. So f0 divides one of g0 and h0, suppose g0 in qx. Now this exercise assures me that f0 automatically divides g0 in zx just because f0 is primitive. To prove this exercise, just imitate the proof of number 2 on the previous board. So clear denominators and use the Gauss Lemma. You should really do this exercise because you have to use the Gauss lemma yourself to appreciate it. You should also prove this corollary of this exercise. It states that the kernel of any evaluation map from Zx to complex numbers is a principal ideal. I stated this in lecture 3, but we were unable to prove it then. Using this exercise, the proof now should be quite easy. Finally, we have an important generalization. In all the proofs that we did here about Zx, the only thing that we used about Z is that Z is a UFT. You should check this. So I have the following theorem. Suppose a domain D has unique factorization. Then the same is true about dx. And I can use this result repeatedly to get, for example, that these rings are UFTs. How do I prove this theorem? In exactly the same way that I did it for Zx. Instead of Q, I use the fraction field of D. And then the same steps stay valid. I can take GCDs in D because D is a UFT. Then I can define a primitive polynomial as before, and the Gauss lemma stays valid. I have the same description of irreducibles in dx as either irreducibles of D or primitive polynomials that stay irreducible over the fraction field. And finally, I prove this theorem. A special case is worth noting when D itself is a polynomial ring in one variable over a field. I know that this is a PID and so a UFT. In this case, the fraction field is the field of rational functions. And I finally prove that the polynomial ring in two variables is a UFT. The reasoning that goes into this case, particularly the Gauss lemma, are useful. So it is worthwhile to do the proof in this case explicitly.